about that. I'm gonna share my screen. How's this week's material gone for you?
Yeah, I don't think it's too terrible. Although, yeah, I just like made notes of where I have questions that I want to ask you,
Yeah.
as
Um,
always.
yeah, of course. I'm gonna show you this is something that I made a little thing when I was taking the class, about after doing extensive studying on this chapter. This was how I broke down the how to decide which reaction it was going to be.
Okay. Okay, I love study guides. Let's see
Yes.
what's on here. Oh, like the solvent stuff and the okay, yeah. Okay, yeah, I didn't even get to SN1. I'm like on that video. I'm like on 5 out of 7, so that's the one.
Yeah, that's right. Have you
So
have you seen any of the elimination yet? Not yet.
no.
That's okay. Do you want to take a picture of this so you have it? I'm gonna upload
Yeah,
this too, but
yeah, I got it.
okay, cool. You'll get there. But yeah, this was kind of like my cheat sheet on like little reminders for myself about how to get through um like, predicting the pathways and all of that stuff. So, do you feel pretty confident with the difference between protic and aprotic?
Uh, yeah, I think so. I like literally just watched that part. It was just like the hydrogen bonding, right?
Yeah, the best way to like tell literally how I think about it is protic proton, right? So
Mm,
there's a proton, a hydrogen in it.
yeah.
So that's the best way that I can like. So if you see like a product, it's gonna be more of like those, um, you know, versus if it was protic, you would have a hydrogen that's on a fairly electronegative atom, like oxygen or nitrogen or something. But if it's aprotic, it's just gonna be that um electronegative atom without the proton, right? Without the hydrogen.
Yeah,
So
that's
another little tip and trick.
okay. Yeah, I'm getting that down. Yeah, okay. Um, yeah, so I just like, can I just like run through where I made
Please.
notes?
Yeah.
So, in the gap notes, page 2,
Hmm.
um, I was hoping you could explain the statement. It's like at the oh, it's like at the 1/3 mark down the page.
Yeah. I'm just also pulling up my gap notes. So I have
Oh, okay.
them. It's alcoholics, correct? Yeah. Okay. You
It's
said page 2.
yeah,
I
it's at
got
the
it
1/3
here.
mark. It was
Like
like
the examples of SN2 reactions.
right above it's the statement that says a stronger base is converted into a weaker base and overall higher energy electrons are converted into lower energy. How do you know that O8, the alcohol part is a stronger base than um the bromine?
Um.
I just don't remember.
Yeah. That's okay. So so a base. Do you remember like what a base is? An acid and
Yeah,
a base.
it has the high energy electrons that it donates.
Yeah. So a bromine. So remember oxygen? Oxygens are very good. I don't think you guys have gotten to like leaving groups. Yeah, you guys have, haven't you?
Yeah.
Okay, so like bromine is a really good like leaving is a really good leaving group because it is happy to have it's 8 electrons with the negative, you know, whereas like oxygen is really strong as far as like coming in, like substituting, it's very strong at doing that. So just like overall, you're going to see bromine being replaced by another, like it makes a really great leaving group. Oxygen has a lot of this has to do with also the energy diagrams. I'm trying to see if I don't know if I have any in here, but like if you look at like an energy diagram of it, um, so here you can see like how we have a much smaller like relative energy, like here's with our bromine. And when we attach our oxygen or OH groups to it, it's slightly lower in energy because the oxygen's electrons are become lower in energy. So it makes a stronger bond
Yeah.
because bromine is larger, so it's a big atom. Remember we talked about this before? Versus oxygen is kind of like a smaller atom. So this doesn't have as strong of a bond, right? So like doesn't have as strong of a bond as it does to carbon. Whereas so it can kind of like kick this off and it'll be happy just
But
chilling
yeah,
with its
that's like my
electron.
point, is that like if it can kick it off easily, that's like the purpose of a base, right? So like a base donates the electron. So I thought because it's so large, then it doesn't hold the electrons as tight, it kicks them off easier, and therefore it should be the stronger base, but it's weaker. That's why I'm confused.
Um, okay, let me think about how you just said that. Base, say what you just said again. I just want to make sure that I'm understanding.
The bromine is like a large like ion. I mean atom,
Mm-hmm.
whatever.
Yeah,
I mean, the bromide ion is large, and therefore, um, like it doesn't
it doesn't
hold,
have a strong of a base. I mean, it doesn't have as strong of a bond, but it's not
like
necessarily
it
that it doesn't.
doesn't like
It's
hold.
not necessarily that it doesn't hold the electrons. It's that the bond isn't as strong because it's larger, so it's farther away. But oxygen, like carbon, can only hold so many. Remember, carbon only has 4. So like bromine can't leave its electrons and go off, and then oxygen also attach its electrons, you know? So so oxygen is coming in and attacking the carbon right here, right? Oxygen's coming in and attacking the carbon because the bond between these lone pairs here would be stronger than the bond between these lone pairs. Where is it? Right here, because bromine is larger. So the bond with bromine isn't as strong.
Okay, so you think about it in terms of the product, and because the bromine doesn't form as strong of a bond, it's what less stable.
Yeah, it's just bromine just in general is going to be a great leap. Like you're gonna see it a lot, trust me. Bromine just leaves. It's a large base. It can carry electrons. So like it's okay to be an anion, you know?
Mhm. Okay.
Um, yeah,
Okay. Yeah, that was just the first thing that I
yeah,
wasn't sure about.
yeah.
And then, um, yeah, also,
Oh, here's this too. This might help. Oh no, this is where no, this doesn't have okay. Never mind, continue. This
oh
is
no,
just showing how it's making
that's like the thing that I'm gonna ask you next.
you're
And
so
so
funny.
don't go anywhere on that
Okay,
page.
sounds good. Sounds good.
Okay.
You're so funny.
So, okay, yeah. That was the next question. I was just getting confused with the like I think I need a refresher on the orbital stuff because Yeah, so do you see the paragraph that starts with, we previously said there is more room? It's about the
Oh,
like orbital overlap. Uh, oh,
okay,
okay,
wait.
yours looks different than mine.
I might
Okay.
not have it on this page, that's why. I just might not have copied it. So we previously said that, yeah, that there is more room for the bromide anion to attack the bromonium ion from the backside.
Yeah. So
Now
if
we
you
look
go,
at the
oh,
backside
sorry.
attack. No, you're
Yeah,
fine.
just
Go
go
ahead.
down a few lines from
Yes.
there. And it says, yeah, it says making a bond requires in-phase overlap. Like
Yeah.
that part is okay, but then it says like
Okay.
we also need to break the bond between carbon and the leaving group in the
Yep.
electrophile. Where
Yep.
are they where are they talking about? Are they talking about the example down below or like,
Yes, yes. That whole paragraph there is about the this right this right here, this whole diagram here that I have. That's what that paragraph is talking about. And so when they're talking about we also need to break the bond between the carbon and the leaving group, they're talking about this right here. We need to break the bond between the carbon and the leaving group.
yeah, so yeah, so I just don't remember how like when all of the I guess I think these are like atomic orbitals, like right, that
Hmm.
are on each of,
Molecular orbital. Well, yeah, these ones are atomic, yep. And then
yeah.
this would be a molecular right here.
So I just don't remember like how does she know to, for example, on the OH, she draws the shaded portion to the right and then says you need that to be
Hmm.
um like overlapping with the shaded portion on the carbon.
Yep.
How do you remember like what the orientation is again of like how does she know that it's going to be oriented in such a way that the shadeds are both going to be, next to each other to allow for the overlap? Like I just don't remember that point.
Yeah, that's okay. So in order for the bond to be made, they have to remember when we had let me see if I can bring it up. All the way up here. I actually don't know how far it is. Oh, this is actually it. Convenient. Um, but let me find.
Like I know they have to match, but I mean like how do you know that they're going to match?
Well, that's the only way to do it. You can't do it any other way,
So
right?
it
Like
just like it's going to be oriented that way because it has
in
to be.
order to, yeah, so you have these bonds, right? I'm just trying to see. I don't know if this is going to be helpful up here, but so remember we have our in phase and our out of phase. So here we have bonding because they're in phase. Remember that the shading is arbitrary, right? So we have these bonds that are made when both of your atomic orbitals are in phase of each other, which remember that that just basically means that um your electrons are in the same area in order to create a bond between them, right? Like
Mhm.
remember that this is a mathematical probability.
Yeah.
Um, that's what that means. When you have your stuff in phase, it just means that they're in this area enough to entangle, so to speak, right? Versus when you have something that's out of phase. So on the other side of this, let's just say that it's over here, right? Because you have two sides, right? Right? So you have, let's just call red out and blue in, right? And so it could be any which way, but so let's just say that this is all part of one, and then this is a part of another, right? So if you have, let me just be consistent here. So if you have these two that come together, there's, let's say, no electrons here, and but we have electrons here, they're not going to create this bond, right? Because the electrons are actually on this side. So there's nothing to interact and create that bond together. So that's why when things are out of phase, out of phase, we call it anti-bonding because we don't create a bond, right? So now let's go back all the way. Let's go back to wherever we were up here, which is, I think, this one. Was this it? Yep. Okay, so now, because we're talking about the bond between, the carbon and the bromine here, and how that eventually breaks to form the bond between the oxygen and the carbon here, carbon has to have their electrons in the same orbital or the same, uh, you know, yeah, I mean, I guess orbital is what's going to say it, as oxygen in order for them to create that bond, right? So we have this space here to create that, which then because of this, we have this anti-bonding, which helps facilitate in breaking this bond because carbon can't have both sides shaded in, so to speak, right? So in order for that to happen, we have this empty space where these electrons can come into,
So
which
like,
then, yeah, go ahead.
you know how in the before the OH attaches, just like in the original molecule, the carbon and bromine are bonded. So
Hmm.
like, doesn't that mean that originally they are in a bonding, like an in phase molecular orbital? So how is it possible that they just like go from in phase to like out of, like, you see how like it
That's,
just like
yeah.
I, like, I don't know.
So
I I'm
electrons must
confused.
go to the lowest energy empty orbital, which is the CBr antibonding. So
Oh, wait, I think I might know. Is it the fact that like, isn't it the fact that there's always a anti-bonding? I thought it was just like there was a comment made like weeks ago that like you can have anti-bonding there, it just might not be filled. Like it could be empty. So it's just like
well,
sitting there.
yeah, yeah, not all of yours will be that original diagram that has like, you've got your things here and then you've got this and then you know what I'm talking about, and you kind
Mm-hmm.
of you add in your atoms as you go, or your electrons as you go. So yeah, so you will have these empty.
Okay. Okay, I think I see. Okay, yeah, and then the bond breaks where it's anti-bonding.
Yeah, yeah,
Okay.
exactly. Yeah, because
Mm.
anti-bonding is higher energy than bonding molecular orbitals, obviously. But if it's the only one that's open, then that would be the lowest empty orbital. Whoops, see what I'm saying? Lowest empty orbital. Because they're going to go into the bonding first before they go into the non-bonding, right? They would fill the bonding first. And however many there was, right? This is if it was just like a 1s or 1s, right? But if there's more, obviously, then you got, you know, P and all that other.
And then can you explain the part about the backside attack? I didn't
Yes.
quite follow what
Yes. So this up here,
uh, it it says. It starts with like this provides the best explanation for. It's like that paragraph.
let's
It's on the
see.
same page, like literally right below the
This
diagram.
provides the best. Oh, right below it. Oh, I just don't have the written stuff. So it says this provides the best for black because the orbital overlap is best at the carbon end of the carbon bromine, where antibonding orbital is largest.
Where
The
are they talking about?
On the back side, they are talking about they're talking about this space right here, where the oxygen is coming into. That's backside attack. Because with a substitution, you're always making and breaking your bonds at the same time. So it's not like what we've seen before, where, say, for whatever reason, I'm just making this up, but say for whatever reason, bromine comes off, right? And then bromine would leave, and then we would have, but we would have a positive, and then oxygen would come in, because then this would have no stereochemistry, right? So it doesn't necessarily matter. This becomes planar by nature, and then oxygen can kind of attack from any which way that it wants. OH, right? Can attack from any which way that it wants. But in this case, during substitution, you are making and breaking your bonds at the same time. So it has to, in order for it to work, your bromine will come off the, say, front, right? So, and as that's coming off, and we see that with these little dotted lines, right? So as the bromine's coming off of the front, oxygen is coming in from the opposite side. That's why they call it backside attack, right? Front and back is kind of like relative, but so that's what they're talking about in that sentence where it says for backside, yeah, because the orbital overlap is best on the end of the new OC bond should form. There is bonding interaction in the transition state, and the carbon bromine bond should break. There is anti-bonding interaction in the transition state. So the anti-bonding is this anti-bonding interaction is that, and this bonding interaction is this.
Yeah, and in the sentence previous, when it says like the end of the CBR where the anti-bonding orbitals are they just talking about like the location where the bromide ion will like dissociate, right? Because isn't that the only anti-bonding? That's the part that confused me. I don't know.
At the end of where the antibonding orbital is the largest. So I think what they're trying to say here is like if we look at this, if we put a line right here, that's the end of the carbon bromine wave function. Because the orbital overlap is best at the carbon end. Oh, at the carbon end of. That's what they're.
It's just like not really at the carbon end. That's why I was confused.
So like, so if you're looking at this and this is the, right, like this is the bromine end, this is the carbon end. The orbital, because the orbital overlap is best at the carbon end. Because if you look, oxygen's not going to come in on this side because it wouldn't overlap.
Okay.
The molecular orbital tells us that the nu should form there, there is a bonding interaction, and that the CBR should break when there is backside attack. Yeah, that's what they mean, the carbon end of the wavelength. So if this is the wave function here, let's just say this is the carbon end, that's the bromine end. So that's what they're saying. It's best to come in from the carbon end, not the bromine end. Also, if it was going to come in from the bromine end, then it would attach to bromine and get carbon off. Does that make sense?
Yeah, I think I see.
I know sometimes the verbiage can be a little confusing. There was something I was having trouble with in the homework site the other day, and I was like, what is this trying to say? But anyway, I reached out to Dr. Pillai and I figured it out. But sometimes that can be very challenging, so don't feel bad.
Yeah. Okay, wait, and then just wait before
Yeah.
we move on from backside, just like in general, something that I struggle with on that point is I think you kind of just explained this, but I want to make sure. How do you know again when um there's the instance where you can have attack from both directions? Like when does that happen?
Yeah. When there's no stereochemistry. Um,
Okay.
oh,
Yeah,
it's right
because
here.
we're
It proceeds via backside attack unless there's no stereochemistry reaction. You can't tell. So, a good rule of thumb is if you see wedges and dashes, if you don't, then you just can't tell where it's coming from because we don't label hydrogen and we can't, like, you just can't tell.
But like, which are the cases when it can attack from either? 'Cause, like, I know this sentence. Yeah, like I understand this example, but I don't know when is the time when like it can go from top and bottom.
Do you mean like what to look for in a molecule?
I just know that like in yeah, in like less in like chapter 4 maybe or so. Like the last few chapters, yeah, there's been an emphasis on like if a molecule uh attacks simply from the backside or if it has the ability to go from top or bottom. And
Hmm.
I feel like I'm very cloudy on the like
It all
how
has to
to
do with
differentiate.
stereochemistry. The only other difference would be your BR2s. When you have, let me see, let me bring this up. Where's my reaction summaries? So it all has to do with stereochemistry, but the only time that it might be a little bit different, you remember this?
Yeah.
Um, so let me see. This one has a front and backside attack. Um, Let me just erase some of this because this is a little crazy. I am going to erase this kind of
Like
this
when
stuff.
it is a backside attack, is
Yeah.
that wait, that's the case when there's a chiral carbon?
Yeah, yeah, it has to do with stereochemistry.
Yeah, I don't know. I get confused, I
Okay,
guess.
so no, that's okay. Um, Let me see. I'm just trying to erase some of this like not necessary stuff. I guess none of it really is at this point, but
You
I
know,
just want to show
that
you
was
like the more
the
common.
most amazing sheet. Like
Good.
that you made that like one time, like the last 2 minutes, you remember? And
Yeah.
literally it has been my lifesaver for the past 2, 3 weeks.
Awesome. I'm glad to hear that. Yeah, that took me about a week's worth of like trying to decipher what I was reading. I'm like, what the heck is going on? And that was like many hours of practice. Oh,
Much
I'm glad it.
appreciated.
Yeah, you're welcome. I'm glad it was useful to you. Um, that's so funny. Um, yeah. So, what was the question? Backside attack.
Yeah, how do you
So,
know?
it all has to do with chirality. It all has to do with stereochemistry, right? The only other thing is like your like syn addition versus anti-addition. Like it has to like this, your H2s are always going to be syn addition, right? Which means that they both come from the same side. But the only other time there's like where you would have some sort of quote backside attack would be when you have the mercury or the Br2s with the CCl4. Um, well, I mean, really any of the BR2s. The reason why is because they're large. And so what ends up happening is, and these rings are a really great way to show it. But when you have this BR, it makes this bond here, but because it's got all these electrons, which I was about to put the positive charge on there, this has got a positive kind of charge, but this has like all these electrons. There's a lot of electrons, right? As you can see. So these electrons kind of make this pseudo bond on this side. And bromine has now, so instead of, because, there's not around that one though. I was gonna say there's bond rotation, but not around that. But like, so if this was, not kind of glued down, so to speak, it would be kind of out here, right? And it could be out here anywhere, because remember that this is an SP2. So then this kind of becomes planar. And so what ends up happening is this would be, that wasn't a very straight line. That's why I'm trying to redraw it. This would be like out here. And this positive charge would be over here. And so bromine could kind of come in from any which way that it wants to come into. It could come in over here, over there, right? Like it could kind of go in wherever it wants, right? Versus when it's like this, because bromine has all these electrons, it's large, it kind of makes this pseudo bond here. So then now imagine that this is the front, and on the back of this same, I'm gonna try to draw it in the same orientation, although no promises. On this same carbon, right? Now we have this over here, there's a lot of steric hindrance, right? That's why we care about stereochemistry. There's a lot of what's called steric hindrance, which just means that there's a lot of electrons in the way. There's a lot of mass in the way, right? But like compared to this side, there's nothing going on. All there is this cool little, and it's, you know, right? Like it's kind of, it's moving back and forth because then maybe this bromine's over here, but then this is now dotted, right? So it kind of, there's a little bit of moving back and forth, right? But let's just say for argument's sake that it's just over here. And then so that other bromine comes in and it attacks from this side because again, this bromine's freaking huge, right? And it's got a lot of lone electron pairs around it. So um, that's why we see this backside attack. So, and the same thing is true here with this merconium thing. It's the same thing except it's Hg, right? Hg just kind of makes these like pseudo bonds. Like it's bonded to one side, but again, because of the free electrons, it kind of bonds over to that other cation. So it kind of takes up. So rather than being on a planar, a trigonal planar type situation, what ends up happening is it's like imagine that if we were looking at it from the side is we have this plane of atoms, right? And so, say you have a carbon atom here and a carbon atom here, and then, these, I just want to make this kind of clear as to like, so these two carbon atoms are, say, these, this carbon, I guess it would be the other way around. Sorry. Let me fix this. So from the side, what it would look like is we would have this, and then these here would be here. These here would be here. And then these here would be here. Does that make sense? And so what we have with this bromine is we have the bromine kind of sitting on top here with this bond, and then this kind of pseudo bond to the other side, right? Imagine that it was on the other side, and then we have that positive kind of hanging, floating around in this space. But that's why we kind of see this coming over here rather than if it was all trigonal planar, you would just have this and you would have, the purple. It wouldn't quite look the same, but anyway, put the purple, the orange, the purple, and then you'd have the other purple, and then you'd have your bromine, right? And then so another bromine could come and attack from any which way it wanted to. Does that make sense?
Don't kill me, but
Oh
I don't know
God.
if you realized it, but like the Zoom like disconnected.
No, I can't stand my
So
internet.
I
Oh my
got
God.
like some of that, and then I got kicked off and I couldn't hear you anymore.
Oh my fuck God. Oh my gosh. Okay.
I'm sorry.
No, it's fine. Well, the good news
No,
is this is
I
recorded.
heard until I heard, yeah, actually, oh yeah, actually, that's true. I can just go back and watch it. It's okay.
Yeah.
You don't need to go through all of that.
No, okay, I'll just give you the short, sweet version, and you can go back and like listen to all my ramblings. But like,
I just
imagine that
didn't hear the part
this
with
is
the
the thing.
colors. I
Okay.
heard the stuff in green.
Okay, so imagine that this carbon here, I mean, this structure here is looking at this structure here, but like from the side. So really we'd be looking at it, we would be, okay, I'm just erasing some of that stuff. You would be looking at it from this way, right? As if like this was the top of your head, and then your chin was like underneath, and these were your eyeballs looking forward, right? In line with the molecule. So now the molecule is on this plane right here. And so this orange atom, so the orange all line up, the lilac all line up, and the purple all line up, right? And so what's happening is this one right here. The bromine, normally, if the bromine didn't do this weird thing where it like attaches here, but then it also kind of attaches over here to this cation while we wait for another bromine or EOT to show up or whatever, OET to show up. What would happen is the bromine would be like this on this trigonal planar type of thing, right? So there would be no stereochemistry because remember, this is still an sp2 hybridized carbon.
Mhm.
Um, so what it would look like is it would look like this over here. It would just be this long planar thing, right? And these atoms would still all line up, but the bromine would be like out here. But what's really happening is the bromine is kind of like up over here because it's attaching, it's kind of being held by the bond here, by this bond here, and then it's kind of got this like pseudo bond that's being made on the other side, on this cation side, right? And so that's why it's kind of being held up in this position. And so that's why the other bromine or the OET will come and attack on the backside because there's no steric hindrance, as we call it.
Okay.
Versus if it was this one where it's all planar, it could come in on either side and it wouldn't matter. Does that make sense?
Yeah,
So the only
but like,
time you really need
what
to
are
remember that mercury, if you see any type of merconium type situation, mercury and then Br2, because it's a big atom with lots of electrons.
so like when you say planar, so yeah, maybe I should really use my model kit more often, but
Hmm.
when I occasionally use it, like when you build the molecules and like they're not like in one plane, like some of them are like, going down, like slanted, up slanted. So like what is the case when it is planar? It's just like the ring part is the planar, or like because like the substituents that are coming off of it are never like in the plane.
So it would be planar if you had three with your I'm getting my model kit. Your model kit. You would get which one's carbon? Is it the black one? Some of them you can't necessarily. Let me put some bonds real quick in my head. Then, yeah, see this we can't make it cleaner. So let's see. Can I make this one cleaner? Wait, real quick then. Oh yeah, no, you can't make this one cleaner either. All right, this one. You can definitely make this one cleaner. I know that for sure. So remember, when you have an sp2 hybridized, you have 3 electron domains, right?
Mhm.
You have sp3 hybridized. You have, wait, did I say that right? sp2 hybridized, you have 3. When you have 3 sp3 hybridized, you have 4 electron domains. Okay. Like, did I say that right? Okay. So here. All right. I forgot I have all this. Oh, we were having fun Monday on Zoom. Okay, can you see this? I don't actually have purple lipstick on. It's just a filter that we did when when we were doing like a Zoom meeting with my student society. Okay, so you can see this.
Yeah.
So
I
this
don't
is,
know why I never turn my camera on. That's so weird.
I know it's so funny, right?
I
I
can,
never
it's
do.
fine.
I
No,
no, it's
no,
fine.
I can, it's okay. I just am like, I'm chilling, it's fine.
I know, me too. I
Yeah.
um I never turn my camera on either because I always look like a hot mess. So because I'm like taking care of a million things and running in here last minute, so that's why I don't. But
Okay, yeah.
I'm gonna put these on here just so it's a little bit easier. Just let me put these hydrogens on here so it's a little easier to see. Mm, yeah, the if you're not good at visualizing things in your head, um, sometimes I am, sometimes I'm not. Like use the models, you know. Okay, so here's our two. Let's see. So here is our sp3 hybridized carbon. See how we
Mhm.
have, sorry, I'm trying to figure out how this camera is viewing this. So if I hold this still and I rotate it around this one bond, this is kind of crappy, but
Mhm.
anyway, you kind of can see this like 3D formation, right?
Yeah,
Hopefully. Okay, you can see this. Yeah, there we go. So
yeah.
versus when I have an sp2 hybridized, let me try. There we go. See how it's like planar? Where like if I rotate it right, everything's
Oh
on
yeah,
like
I
one
see.
plane.
Yeah.
So this would be an SP, and then when we have it like this, then it's like all it's in line with my hand. The plane is in
Mhm.
line with my hand, versus like this. Now the plane is perpendicular to my hand.
Mhm.
So that is, why was I telling you about this? Oh, this would be what I was talking about when I was mentioning the plane. If the BR did not attack the um the cation, cation. If it didn't attack the cation, it would look like this, where it was kind of sticking out of the plane. But it doesn't. It makes that 3D, which now I don't have a 3D thing to like show that, but what you would end up having is, let's just say these bottom hydrogens here, these bottom hydrogens here are
Mhm.
on one plane. What you have is this. This isn't literally what it looks like, but I'm trying to show you with this atom. Then you would have the bromine kind of on this side, and that's why it makes it easier why you would have that backside attack, so to speak, on those BR2s.
Okay.
Does that make
Okay.
sense?
Yeah.
Kind of a shitty, I mean, a crappy, um, a crappy thing, but hopefully that helps give you a little bit of a
No,
visual.
it's good. It's good. It's good.
Okay.
Yeah, but like still on the stereochem point,
Yeah.
on page 4 on the top.
Yeah.
Yeah, so one thing that I didn't understand was so like do you see how in the first example like the bonds they like move over like they shift but yet the what is wedge remains wedge and what is dash remains dash.
Hmm,
But
hmm,
then
hmm.
yeah, but then in the other examples like um that's not the case. Like the wedges become dashes and the dashes become wedges, and I don't know what is the difference or like why that happens in some and not others.
My dog, sorry. Um, so okay, let me find this.
Yeah, it's that page. Wait, no, wait. It's the one
Oh,
you're
this
on.
one
That one, yeah. So in the
up near
first
top.
one, yeah, so like you see how like in
Oh,
yeah, so like in the first example, Like they remain and then in 2 and 3 they flip-flop?
Okay, yes, because of where you're attacking from. So, oh, crap, out of my way. So with this top one, how the wedge remains wedged and the dash remains dash. I'm like, what am I trying to say? And the dash remains dash. So this is because you're coming in again. Try to imagine this like a plane for a second, even though it's not because this is a 3D molecule, right? But just try to imagine it like a plane for a second where there's one here, there's only like one way for it to go, right? But now with this one, imagine that your plane is now, how do I draw this? Imagine that your plane is now like here. Let me see. Imagine your plane is now here and your bromine's coming out. Let me see, and your bromine's coming out of it. So what's happening is it's being attacked from the backside of bromine. So it's coming in from this side of bromine. And so what's happening is this hydrogen then has to be pushed forward because we're coming in from the opposite side. And the same thing is happening here. It's hard to imagine with like the planes. It's probably not a good example. And the same thing is happening here on this backside. So our bromine is wedged. I was trying to think if I could come up with an easy rule for you to remember. So we have to come in from the opposite side. Now just remember that whatever you do, you have to come in from the opposite side of your leaving group. Okay, so it's the same thing with this. Like we're coming in from the opposite side. Let's just put the plane here. We're coming in from the opposite side of our leaving group so our leaving group can go. So in the same way, that's this example right here, right? But in this case, because bromine is coming out of the page, that means that we have to be coming from underneath the page. But the hydrogen is going into the page right now as a dash, right?
Yeah. Yeah, I
So you
follow.
have to push that hydrogen up out of the way.
But the bromine is leaving. So
Uh-huh.
doesn't that mean that there's more space? Okay, wait.
For the
Okay, wait.
hydrogen to move into that space.
But how do you know that the group, the OCH3
Hmm.
is gonna go on the bottom?
Because it has to. It's going to take over the space where
Oh,
hydrogen was.
wait, because the bromine is already on top, so it obviously can't come from the top because they collide.
Right. Right.
Oh yeah, yeah, I get it. Okay. Okay, and
Yes.
then like so then in example 3, then the bromine is on the bottom. Okay, so then the other one has to come in from the top.
Yes.
Okay, okay, okay.
Yes, you're getting it. It's
Yeah,
clicking.
okay, I see. Yeah, I was like, oh, okay, okay.
Yeah.
Okay, and then
Yeah.
in number 1, um, the bromine is in the plane.
Yes.
Okay, so then this is an instance where, yeah, it's backside attack. And so now the new substituent is in plane and then everything else shifts around.
Yeah, it just gets shifted
Oh,
forward, but it doesn't necessarily change the orientation, right? Versus in the other ones, because bromine is coming out of the plane, I want to make a rule for you, but I'm nervous too because I don't like to be wrong, obviously. But perhaps a good rule of thumb to see if this works as you're going through your homework problems
mm,
is to see if bromine is in the plane, then your substituents that are in or out of the plane, right? Your
mhm.
3D substituents, so to speak, won't change. If bromine is into or out of the plane, the other substituent that's in or out of the plane will replace the bromine, and the new nucleophile that's coming in will
Mhm.
then take the place of the other one. Does that make sense?
No, yeah, I know. I totally I see it now. I totally did not get this before, but you just explained it so well. Okay, yeah. Okay,
Okay.
yes. Yes.
Yes.
Okay, it is happening. All right,
Okay.
good.
If it doesn't work out 100% of the time, though, I'm giving you the forewarning now that like it's just a guess. And I think it'll work, but just check it out in your homework problems to make sure, because I could be wrong. But I think
Yeah,
that's the
and
best way to explain it.
like with the so from last week with the like enantiomers and things like that, um, I had a really like hard time like visual like I don't know figuring out like with the R and the S stuff, not to go backwards, but like now that we're on the stereochemistry point,
Yeah.
um, like how do you know like what's the intuition for like you know if like two things are like enantiomers and then one is like going to be an R, like how everything is opposite, like if it's all R's then they all become S's, for example, like
Mm.
do you know why that occurs?
Yes, but I didn't review it, so now I'm like, oh, what's the
Sorry.
rule? No, 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 it's fine. Yes, and there is like kind of a rule with that, right? It's like if they're all S and this becomes R, and if they're one S and one R, then the other one is this and whatever. What
You
is the
see,
rule
do you
for that
see?
one?
That's the problem with you being a great TA is that I like I think that you know everything all the time.
I don't, I
So
promise. I
no,
barely know enough to come onto these office hours some days. I'm like, oh shoot, I hope they don't ask me any questions.
yeah, well, unfortunately, Jackie always shows up and
That's
so
all right. Keeps me on my toes.
sorry.
Keeps me on my toes for sure. Okay, just remind me what section that's in. Oh, okay, enantiomers. I found it.
Yeah, it's
Just
like
I just
from
happened to roll to it. Okay, let me just look real quick, see if I wrote it down in my notes. So enantiomers have opposite configurations at all chiral centers. Diastereomers are stereoisomers that do not have opposite configurations at all chiral centers, since they are not mirror image isomers, excuse me. So if all of their chiral centers are opposite, S or R, S, whatever, then they are enantiomers.
yeah. I just don't like why is it like okay, my like difficulty I guess is just like I don't know. I don't know. Like, so like if you just take the mirror image of something, you're not going to be changing. Like if something's pointing up, it's still going to be pointing up, correct? And like if something's pointing down, it'll still be pointing down because just like the mirror image. But
In
what is
plane, you
what?
mean? In the plane, you mean? Or
No, like wedges remain wedges and dashes remain dashes.
oh, okay. I get what you're saying. Mhm.
But like that's the way it looks. I'm just looking at like the example when they showed like what an enantiomer is, and they're just talking about the mirror image. I guess is like the rule that wedges remain wedges, dashes remain dashes, and then the in plane stuff just like they're still in plane, but now they're flipped. So I guess that's what. So I guess like when you're reading the clock, that's why it's R becomes S because like then you read the clock the other way. I guess I don't.
So, well, and especially when you have a single bond, remember that there's 360-degree rotation. So that's something that like, that's definitely something, although I know this was last exam, that was really helpful to have these things for,
Yeah, and I didn't
because
use it.
I mean, hopefully you
At
got the
all.
answers right.
I still got 100 on the auto graded. and
There
I
we
didn't
go.
use it.
Th-
So I
There we go. Yeah, no, that's good. Some it's like very easy to like kind of figure that out, and others it's like you're like, what the heck? But yeah, so when you are turning or when you're trying to figure out like your R's versus your S's, is that yes, you have to look at that central carbon. And I always imagine in my head looking at it from like if there was another carbon attached right here, wherever it is, right?
mhm,
And like
mhm.
I always imagined, this is so crappy because I don't have a molecule made, but hopefully you can kind of work with me on this. But I always imagine like looking at it from this way or this
Yeah.
way, it doesn't matter,
Yeah.
whatever. And then like reading it, whatever your highest substituents are, reading it that way. So if your mirror images are the same, I mean, if they're mirror images, then they would have to be opposite because you're reading them from opposite ways.
Mhm. Yeah. Okay. So yeah, yeah. But like the stuff that's like in plane, out of plane remains in plane, out of plane. I think you're just,
Yes.
yeah. Because you're not, but then okay, but the thing that really confused me is
Because
where is it?
imagine that, let me just switch a couple of these out real quick just so you can see the difference. Because imagine that you have this carbon and you're looking at it from this way. I'm trying to find a way. You're looking at it from this way. And now imagine that that's same exact carbon, it's a mirror image, right, on the other side. But so then you have to look at it this way, right? So then it flips its orientation,
Mm, okay.
because
Yeah.
if it's mirror image, that means everything that's coming out of the page will still be out of the page. But if you're looking at it from this way versus that way,
Yeah.
then it would be opposite.
Yeah. No, I see. I'm just trying to find it's my own fault that I have questions on this because I didn't go to the last office hour, so I can't even complain.
I was shocked, to be honest. I was shocked.
Yeah,
There was a
sorry.
lot of people that came, but I was like, wow, Jackie must feel confident.
Oh, it wasn't that. I was just so like tired.
I listen, I hear
Yeah.
you.
So yeah, honestly, then on Saturday I regretted that decision very much. So
I'm sure you did fine. I'm sure you did fine.
no, I somehow did. I don't know, like the entire day I was very stressed. So yeah, you know what? I won't do that again. Um
Well, here you are. You've got one more chance of
redemption, yeah.
yeah. What is this Chem 233 or something? So
Uh-huh. Yeah. Okay, wait. And then one more thing on this
yes,
point. There, I'm just trying to find it.
on the diastereomers and the enantiomers
Yeah.
and all that.
Yeah, last week's stuff. Um, wait, what the heck was it? Was okay. Yeah, so I was confused on when there's the like rotation around the single bond, how does that not change the like on page 7? It
Of chirality.
yeah. Yeah, it's yeah, I think this is chiral. Yeah, it's
Yeah.
chirality. Yeah, at the bottom of page 7, it's asking for the relationship between the two structures. And um I am still confused on this because like there's rotation around the single bond and like meso compounds rely on there being a plane of symmetry.
Mhm.
But like as soon as you rotate around a single bond, you're gonna change the stereochemistry. So then how do you truly identify that as like a meso
You,
compound?
you have to rotate it until it is the same or in the same plane. So that's the part that sometimes can be very tricky when you're first kind of looking at some of these, um, because you have to be able to kind of like rotate that in your head. Um,
So anytime that like you can rotate, like you can make a single bond rotation and come up with a plane of symmetry, you automatically say it's a meso compound.
mhm. Yeah,
Okay.
because they're just always kind of moving around. Remember, these are just in the moment representations of these atoms, like they're never really like constant. So
But you can't do that for just like
double
a
bond.
pentane, a cycle of pentane. Like if it's a ring, you cannot.
Because it's yeah, because now you have like two anchors.
Got it. Okay, okay,
Yeah.
okay. Let me see. And yeah, because there was a question on the test, um, that I just like wasn't sure about. It was regarding like which one is an enantiomer, and it showed like I think it was like a cyclohexane or something, and it's just how like methyl groups all the way around it. Some methyl
Yeah.
groups were dash, some were wedges. And the option I went with was just the one that changed the orientation, like made all the wedges dashes and dashes wedges.
Yeah.
Um, but I just like, I don't know, I just wasn't sure about it because do you automatically switch everything? I don't know. Like in my
So
mind, I was
remember
like, is that like a double
enantiomers?
negative?
No,
Yeah.
enantiomers have different stereochemistry at every chiral center.
Different stereo. Yes, because it's like the mirror image thing.
Mhm.
Yeah. And okay, so maybe I got it lucky. I'm not sure, but I don't know. Like that's the thing. I was sitting there and I wanted to do the R and S thing, but I didn't have the time to like sit there and it would have
Figure it
taken
all
way too
out.
long.
Yeah.
Yeah. So so then it was just like switching wedges and dashes not a good idea.
Sometimes it can be in like you said, in like a ring, that would be helpful because it can't turn. But when you have something that's uh like I don't necessarily have anything here on the screen, but when you have something that's, let me just make some space somewhere. If you have something like this and you've got wedges and dashes, it's not necessarily a good idea because let me make sure I draw this correctly. Um, for whatever it is, it's not necessarily a great idea because these this there is that spinning, there's that rotation. But if you have something like this and you've got a wedge and a dash, this can't rotate because it's anchored here, right? So, and this is your chiral center. So then you could just switch it, as long as obviously your substituents were, correct, right? But you could just switch it, and then that would be for that chiral center, that would be an enantiomer because
So
you
you
can't
either
rotate.
so you either do the mirror image or you keep it as is and you switch wedges and dashes.
You either do the mirror image or you keep it as it is and switch
Yeah.
wedges and
To
dashes.
like make an enantiomer, like if you take the mirror image, you keep the wedges and dashes, dashes, but you just like mirror image the molecule.
Mm-hmm.
That's like option one. Or the option two is that you keep the molecule as it is, but all of the wedges become dashes and vice versa to switch the stereochemistry.
Okay, let me think about that. So if you had, I want to use this example on chirality so we can try that. I don't want to say yes for sure until I know. Um, Is this chirality? Let me see. We have chirality here somewhere. Action summary. Okay, so yeah, this is a good one. Okay, so if we did, oops, I'm gonna draw this. So if we had this, carboxylic acid, and all we did was switch the wedges and the dashes. Oh, wait, that's what they did in this one. Oh no, because they have it up here, that's why. So if we just switch the wedges and the dashes, then that means that this becomes a dash, OH. This becomes a wedge, H, whatever, you get what I mean. Then this would be CO2H, and then this would be H, and this would be the NH2. Is that the same thing? Now, if we looked at it from this direction, this would be 1, 2, and 3, right? Carboxylic acid has, no, the other way around. Oh,
No.
because that's an N, yeah.
Yeah.
Okay, so it starts with a C.
Mhm.
1, 2, and 3. Let me change the color so I can see it. 1, 2, and 3.
No, it says,
Oh,
wait, I thought the hydrogen was 4 and that's it's like the other carbon that's, oh, maybe you're labeling it that way. Oh, I don't know. Okay, never mind.
yeah, I was labeling it that way because if we look at it from this direction. But
Yeah, yeah,
yes,
yeah.
I
Yeah,
mean, if you,
sorry.
no, that's okay.
It's the same.
Yeah, I mean, if we looked at it from this way, then we could say this was 3 and this was 4, and then we would just look at it from this direction. So, and if we did it that way, this is behind. That got me all screwed up.
No, yeah, so then it is one, it's 1, 2, 3, but then it's actually S because the hydrogen is a wedge.
Yeah, so if we're looking at it from this direction, then that means that nitrogen would be on our right. So we would be right, down, and left.
Wait, how do you know nitrogen is on your, oh yeah, yeah, right down, oh yeah, yes, okay, never mind, yeah.
Yeah, yeah. So then nitrogen would be right, down, and left. But S is counterclockwise.
Yeah, uh, yeah, because the hydrogen is a wedge. So you reverse what you would have said.
Right. That's where I would always get it mixed up too. I was like, oh wait, that's what is going on. Yes, because we'd be looking at it from the other way. It's wedge it's coming out of. So if we put this 3 here, right? Okay, that's why. Yeah, so yes, 1, 2, and 3, but it's the opposite because hydrogen's coming out of the plane. So yes, then this would be S, and then this is also S because it's 1, 2, no, the other way. Carbon, wouldn't this be 2 though? Because this is carbon, carbon, and this be 3?
Methane is mm, it would be 1, it would be the methyl would be the 3. Yeah.
Yeah.
Yeah, so that would be 1, 2, 3. So that would be S as well.
Oh, right. I'm like, I've been thinking that this was supposed to be R, and I'm like, but this is not an R. I'm so confused. That's right. This is we are looking for an S. Okay, yes. Okay. Yes. So it works. It works.
Yeah,
Mhm.
I think I came to a realization of what the difference is and why I was confused. So I think it's just the fact that um in the one on page 7 that is the meso compound,
Yes.
like So the plane of symmetry thing is your surefire way in the sense that the only way it's going to be symmetrical is if you have all the same substituents. So you can still have rotation around a single bond in other cases, like in enantiomers, for example, but it's not going to be, it's going to be an enantiomer just because all the substituents are different. I think that's what confused me. I was like, I don't understand like how you know with rotation around a single bond. You can do that all the time, but the meso compound's just special because they all have to be the same. Whereas the enantiomer can have different substituents and you can still rotate it and change. Um, I believe. I,
Well,
actually no. Because if you rotate though around a single bond, then you are gonna change the stereochemistry.
well, you don't change the stereochemistry around that carbon. You're just changing the setup of the molecule. So the stereochemistry around those carbons aren't going to change. So
How is that?
so in this, if we rotate it, which is what we just did, in this one, instead of drawing it like this, we just rotated this one turn this way
Uh-huh.
so that we had our CO2H over here, carboxylic acid over here. But that didn't change our stereochemistry.
But then I thought the NH2 was gonna become a dash and the H would be a wedge.
It does, but that doesn't change the stereochemistry
Wait, how do you know that?
because it's still in the same orientation. The orientation, the stereochemistry has to do with the orientation around that molecule, around this molecule. It just has to do with the orientation. So again, if
Wait, when you say
we,
orientation, do you mean like the order in which they are next to each other? Or you mean if they're a wedge or a dash?
I mean the order in which they exist next to each other, not
Okay.
whether or not they're a wedge or a dash.
Okay.
So let me just build this out real quick. So if we have, oops,
Yeah, but I feel like they are different. Maybe I just am not seeing this, but in the one that's in the book, it
the
goes
drawing is
C.
represented differently, but it's still the same thing. Okay, go ahead.
So, like in the one in the book, you have the carboxylic acid in the plane, and then if you read it like a clock, then you hit the amine, right? Whatever that is, NH2, and then you hit the hydrogen. And then when you rotate it around the single bond for the one you drew in blue, then you have the hydrogen amine carboxylic acid. So they're in like a different order when you read clock
Um,
forms.
okay, wait. So on here for this one, well, these are diastereomers, so that's not even the same thing. So for this one, our enantiomer, right? This is what you're talking about, this one?
Yeah. Uh-huh.
Okay, so we have this orientation. This is the enantiomer of it, right? But so we have this right here, but it also equivalent. I'm just going to draw it on me. We decided equivalent also is going to be right.
Mm,
All we did was flip the wedge and the dash,
yeah. Mm-hmm.
right? The reason why the NH2 is the amine is on this side as opposed to this side is for consistency with drawing, because you're supposed to put your dashes on the same side as your wedges, right? That's why. That's the only reason why it's flipped around. Does that make sense?
Okay. Okay.
See how,
So,
yeah. See how this on this drawing, on these drawings, I should say. See how we
mm,
have our wedges are on the right. Our wedges are on the right side, versus our dashes are on the left. That's why I switched the NH here, the
Yeah.
NH2, I switched it. So just to make that clear, but go ahead.
Yeah. Um, yeah, so if you look at the molecule on the left, in the,
Yep,
like the one that's printed, so
yep.
just say we rotated the single bond, um, maybe this is just a wrong understanding from my part, but I thought that if you rotated that, then like the hydrogen, um, like it's currently down. I thought it would be up. Like I thought that like the wedge would be a dash, and then like the dash would be a wedge. So, but then if you look at the molecule on the right,
Mm-hmm.
um, the hydrogen is still dashed and the NH2 is still wedged, even though we rotated. How is that?
Mm-hmm. You rotated it, so then that's why. If it had stayed in the orientation right here, if it had stayed in this orientation where you have your planar like this, right?
Mhm. Yeah.
This orientation, then
Uh-huh.
you would have your NH2 dashed and your H wedged. But because we changed the orientation of our plane, we now have to flip this.
Wait, how did we change the orientation of the plane?
Uh, See how we have this? This is the orientation of our plane. Remember, this is full, there's like full
Oh,
360 rotation versus this is our plane here.
yeah. But I thought so, yeah, so I thought that the way that the carboxylic acid just flipped, like I thought like if you're looking at the line of symmetry or the like say the plane is purely horizontal, so you're
Yeah.
flipping. No.
No, no, say, I'm saying yeah, because
Oh,
I'm
oh,
listening.
sorry. I thought you said like no, as it's like not correct.
No.
So um I thought that like when you're rotating around the bond, you're imagining that the horizontal is like your plane. And so when you rotate, that's how the carboxylic acid goes from being in plane in on the bottom, like pointing diagonal, like southeast, to now pointing northeast. And then I thought that the hydrogen and the NH whatever would also flip, but I thought in doing so, the wedge and the dash would reverse.
So remember that these are two different molecules. These two are enantiomers of each other. Now, if we were to take this molecule with this type of orientation, then you're right, we would have the hydrogen like this and the nitrogen like this.
Oh, but then it would be the same. So when I'm describing it, it would be the exact same molecule. It's just rotated.
Yes, yes,
Ah,
yes.
I get it.
Okay.
Oh, it's
And
so
that is
satisfying.
okay, good. And that's why, as you were talking, I was building this molecule out to try to show you the difference. So when you have these, so you have your hydrogen is, see how these all have different colors, right? So you
Yeah.
have your hydrogen. I don't know how to take like my background off. What are you doing? Help. Where's my freaking video? Okay, this is not helping. Hang on one second. Oh, there we go. Video. Choose virtual background. Off for a second. Okay. So we have a hydrogen that is out of the plane on the left side. Okay. My camera is also mirrored. So I have to try to. So is this hydrogen right here the same as the one on the left here? Is this hydrogen your left? Is
Yeah.
this side,
We
this is your left?
Oh yeah.
Okay, perfect. Okay. So this is the hydrogen. This
Mm,
hydrogen right here is this one right here.
mm,
Okay. And then we have the blue back here is the OH, and the red, no, the green, the green
yeah.
is in plane. Okay. So then
Mm,
we have the other one. This hydrogen is in back.
mm,
Um, and then we have the NH2 and the carboxylic acid, right?
yes.
And so if we were to just turn the molecule so that our hydrogens, or that our two pieces here, right? So if our what, CH3 and carboxylic acid, right? CH3
Mm,
and carboxylic. If we were just to turn it so that they were both in the plane but up top, now you see how our hydrogen are both coming out of the
mm,
plane here,
I see.
versus when we
Cool.
have our stereoisomer, you would have this would basically come apart and go this way. I'm not going
Mm,
to totally rebuild it, but hopefully you can kind of understand
yeah.
that. And so then when you have this has both of the oxygens coming out, or into the plane rather, and it has your CH3 and carboxylic acid, or the other way around, right?
Mm,
Up here, then they're both on the same side into the plane again,
I
which
see.
my fingers are in the way, sorry.
Yeah.
Right? Does that make
Yes.
sense?
Uh-huh.
We've changed the
Yes.
orientation.
Okay, yeah, no, that actually that makes so much sense.
Okay, hopefully.
Yeah. I struggled on that test for no reason then.
Yeah. That's why I'm saying like I always had, to be honest, um this was how I built my structure. I just had different things on all of them. Um, and I would just like label them on my paper, like, oh, green is this, red is this, red is this. And so as I would turn it, I would be like, oh, okay, that's, it was like a little bit easier than to try to say, like, all right, now if this is here, whatever. So anyway, that was just something I did that kind of helped me. But I don't know as you'll really have to like, you'll deal with structures a little bit more in OChem too as well, but not too bad. So
Okay.
hopefully that helps with the chirality piece of it. So yes, I guess then if you wanted to create your rules of thumb, which is a bad turn of phrase to use, to be honest, but um, if you wanted to create your rules, um, if your plane orientation stays the same, then you can just flip your wedges and dashes.
Hmm.
But if your orientation is now different, right,
Yeah, then you got to
then you
keep
would
them.
then you would keep them the same.
So I did get that question right, kind of luck.
Yeah, kind of luck.
Well,
Yeah.
good. I'm not gonna complain about that.
Hey, take a 100 anywhere you
Okay,
can get it, right?
wait, hold on. I'm writing that. Okay, wait. You flip the plane. I mean, yeah, you flip the, no, you keep the plane, you flip. Yes.
Yes. If you keep your substituents in the same planar order, like top and bottom, or both top or both bottom, right? If
Mm,
your if the planar structure stays the same, then you would
mm,
flip your wedges and dashes.
yep. All right, beautiful. Okay. I seriously got to start using this model kit.
I know, I
It's
felt like I really
foolish.
didn't use
It's
it a
like
lot.
literally foolish not to. Whatever.
It's helpful when you're doing the like, have you guys dealt with the cyclohexene? Yeah, you like the chair conformations and stuff. Sometimes it's like
You
wanted to
know,
use it for that.
I still can't do a Newman structure, I'll be honest.
Oh gosh.
It's humiliating. I was doing the homework and yeah, they were doing Newman. I was just like,
You're like, I give up.
I don't know why it's so hard for me. Anyway, I'm sorry. I always keep you so long.
It's all right.
No, it's okay. I gotta finish videos anyway, but I will probably return tomorrow.
Okay. That's a good stopping place for you.
Yeah, no, it's okay. I feel bad when it goes over an hour and a half.
No,
So
it's all
it's
right. I
okay.
mean, if you got one more thing you want to cover, I'll give you another 10 minutes. Fine. Then I have to do my own biochemistry
No, no,
homework.
it's okay. It's okay, really. I'm good.
Are you sure?
You go ahead. Yes.
I don't
Thank
want to. No. No, I'm just kidding. I do because I just want to get it over with, to be honest. I'm like ready. I am ready, I tell you, because I can't. Just want it to be done.
Sorry. I don't know how you're doing all this, to be honest. Like, I say I'm tired. You should be tired.
Oh my gosh, yes. I'm highly exhausted all the time. I actually don't drink that much coffee. I used to never drink coffee, but now I do have a 1 cup. I limit myself to 1 cup a day.
That's my problem. I don't drink any, so
Yeah,
that's
that was how I used to be. And then I had kids, and I was like, it's now my lifeblood.
well, you know what? You do what works, huh?
Yeah, exactly. I know. There's some days where I'm like, oh, I really want a second cup of coffee, and I have to remind myself that too much caffeine is not good.
Not a good idea.
Yeah, no.
Sarah, as always, thank
Thank
you.
you. Yes, of course. Thanks for coming, and I'll see you tomorrow night, 8 p.m.
Yes, you will.
Good
All
luck.
right. Yeah, see ya. Bye.
Bye.